Here are the solutions for the midterm diagnostic. Hopefully you'll just be ticking away all your solutions. Question 1, we've got a sequence, -5, 5, -25, 125. Part A, why is the sequence geometric? Our test for whether a thing is geometric is whether the common ratio between successive terms is the same. Okay, so I should get the same result dividing those terms. Remember, this is T1, T2, T3, T4, etc. So divide the first two terms. 5 divided by -1 gives me -5. And divide the third and the second term. -25 on 5 equals -5. Okay, so why is the sequence geometric? Okay, sequence is geometric as there is a common ratio between successive terms. All good? Okay, so that was part A. Part B, determine the 20th term of the sequence. Okay, so I'm trying to find what T20 is. Okay, find T20. So I'll have a go at that. I know that the first term is -1. I know that the common ratio is -5, and I know that I can find the general term by this formula. So to find T20, it'll be the first term multiplied by the common ratio in brackets to the power 20 minus 1. Okay, and we'll go to our calculator and do that. Alright, so I put in my calculator and I get this weird value. A lot of people asked me what this meant on the exam. Okay, 1.9 e plus 13 means 1.9 times 10 to the power positive 13, which is essentially a really big number. Okay, but that's the term. It would mean move the decimal place 13 places to the right. Okay, having a look at question 2. In geometric sequence, the fourth term is 24, the ninth term is 678. Determine the sum of the first 50 terms. So what I know is that the fourth term is 24. I know that the ninth term is 768. I know a formula about Tn. Okay, and I'm trying to find the sum of some terms. I know some formula about the sum of terms. Okay, what do I need to find? I need to find what the sum of the first 50 terms are. Alright, let's see how I can play with this information to find S50. So I see to find S50, I'm going to be subbing n equals 50 in here. I need to know what A and R are. Okay, so T4, I know it's 24, but I could use my general formula and I could write it as AR to the power 4 minus 1, okay, or T4 is AR cubed. With T9 I could do a similar thing. T9 is AR to the power 9 minus 1, okay, or TR is AR to the power 8. Okay, I know that T4 is 24, so I can replace this T4 with 24. Okay, and this will be my first equation. Similarly, I can replace the T9 with 768. Okay, so I've got two equations and two unknowns. Okay, I don't know A and I don't know R. I'll try to find them both at the same time, okay, simultaneously. So I'll take equation 2 and divide it by equation 1 and see what happens. So equation 2, 768, and on equation 1, 24. And do the same thing with the right hand sides. A out of the power 8 on AR cubed. Doing some simplifications here. If I do 768 divided by 24 on my calculator, I'll get 32. And using my index laws, the A's are going to cancel each other out. And I'll be left with R to the power 5. So to find R, I'm going to find the fifth root of 32. Okay, in this case, there's no plus or minus out the front of that because it's an odd power. Okay, and the fifth root of 32 is 2. So I found R. I should be able to find A now as well. So I'll sub R equals 2 into equation 1. So 24 equals A times 2 cubed. Okay, subbing it in here. Okay, just replacing R with 2. So A is 24 on 2 cubed. And it's just a calculator exercise from here. Okay, so 24 divided by 8 should give me 3. Yep. Okay, so what I really should have wrote in between these two is that I need to find A and R, okay, to guide myself through the solution. So to be able to find S50, I need to find A and R. Now that I've done that, okay, I can find S50. Okay, so subbing all these points in. So I'm going to sub in A equals 3, R equals 2, okay, to find S50. So in this general formula, 3, 1 minus 2 to the power 50, all divided by 1 minus 2. Again, ends up as one of those scientific notation solutions. It ends up as 3.38 times 10 to the power 15. Okay, and then at the end of it, I'd make sure I write some sort of statement. Sum of the first 15 terms is 3.38 times 10 to the power 15. Okay, always make sure you can make some concluding statement there. Question 3. How many terms of this sequence are required for the sum of the sequence to first exceed 1 million? Alright, so I'll write down the things I know. Let's have a look at that. I know that the first term is 0.1. I know that the common ratio is going to be whatever the ratio between the first two terms is. Okay, and I'll just double check that it works with the next pair of terms. Yep, so I know A is 0.1, R is 10. Okay, what do I need to find? I need to find when the sum of some terms, okay, is bigger than 1 million. Okay, so bigger than 1 million. Okay, I've got a formula for the sum of n terms. I'll write down that formula. Hopefully we're getting good at these formula by now. Okay, and I'm going to essentially substitute all these values in. So even though I'm after when it's bigger, I'm just going to solve for when it's equal to 1 million and then do appropriate rounding. So I want the sum of the terms, okay, to be 1 million. Put that on the left hand side. I know that the A value is 0.1. 1 minus R is 10 divided by 1 minus R. Okay, so from here, if I can solve this for n, I'll have an indication of when the sum of n terms is greater than 1 million. Okay, so I'll just keep the million on this side for the moment. All I'm going to do in this stage is make my life a little bit easier by, instead of writing 1 minus 10, put a -9 there. Okay, from here, I'm going to multiply both sides by -9. Okay, I'm trying to get the n by itself. Need to get rid of this 0.1 as well. Can't convert to logs when I've got something on that side still. Okay, so from here, trying to find what this unknown power is. Alright, so I did make a small error in here, and it actually did feel weird along the way. From here to here, my power seems to have escaped outside of the bracket somehow. Okay, so this power of n should be inside the brackets. Okay, and this power of n should be inside the brackets here. Okay, the reason why I realized it was wrong was because in this section here, I would have had a power of -9, and when I convert to logs, I would have been in all sorts of trouble. Okay, so that power needs to be inside the brackets. Okay, but since we're not multiplying it by anything anymore, we no longer need those brackets outside it. Okay, so a few more, I guess, steps to go. I might simplify this thing on the left-hand side, okay, just to make it a bit easier to deal with. So -9 million divided by 0.1. Okay, so I've got -90 million now on this side. Equals 1 minus 10 to the power n. I need to get 10 to the power n by itself. A few different ways to do this. You could subtract 1 and then divide by -1. Okay, in this scenario, I'd probably bring the -9 million to the other side and bring this -10 to the other side. So I end up with 10 to the power n equals 1 plus 90 million. Okay, or 10 to the power n equals 90 million and 1. Okay, so from here, okay, always running out of room, I can convert to a log statement. Okay, so this unknown power is something with base 10, and I need to get to this big number. I'll type this into my calculator and see what I get. I end up with 7.95. Okay, so I'll put this down here, 7.95. When I look at these terms, they're always getting bigger. So 0.1, 1, 10, etc. If I only had 7 terms, then I'm not going to get to 1 million. Okay, so I'm going to write some conclusion here that I need more than 7 terms to get the sum of 1 million. Okay, therefore, okay, you can put a little dots in. Therefore, need, go away, go away. There you go. Need 8 terms. Okay, this little part in here is key because it shows how you've justified your rounding. Moving on to question 4. Okay, how could I check this answer's right? By the way, I could just find, so as a check, I could find what S8 is. Okay, just to show that it's more than 1 million. That's only if you've got time in the exam for C&J purposes. Question 4, a stone is thrown, so it skips across the surface of a lake. So here's my lake, standing on the side, I've got a stone, I'm going to throw it, and it's going to skip along the lake. Okay, basically bouncing along the lake. The first skip is 5 meters in length. Okay, so 5 meters for the first skip, then 3.5, then 2.45, and then so on. What we need to find is if the stone keeps on skipping, how far across the water will it eventually travel? So that doesn't tell us how many skips there are, so we're going to assume that there's an infinite number of skips. Okay, so let's have a go at this. Our sequence is 5, 3.5, 2.45. Okay, so what do we know? Know that the first term is 5. Know that the common ratio is 3. First term, correction, second term divided by first term. Okay, and verify it with third term on second term. Okay, hopefully both of these end up the same. If not, we can't solve the problem. Okay, we're in business. 0.7's all the way. Okay, what do we need to find? The sum of an infinite number of terms. Okay, formula for the sum of infinite number of terms. Okay. A divided by 1 minus r. I know A is 5. I know r is 0.7. Okay, I should have the distance of 16 2/3 meters. Okay, and I can write some statement down the bottom here. Stone will skip 16 2/3 meters in total. Okay, so that's part A done. Part B is state any assumptions and their associated effects required when solving part A. Okay, so as we sort of talked about in the first place, okay, I've assumed that the stone will keep skipping indefinitely, and I've also assumed that the lake is at least 17 meters in length or width, whichever one you want. If these assumptions are not correct, okay, then the stone will not travel this distance. It will be stopped at an earlier distance, at a shorter distance. And shorter distance. Good drills. Question 5 is about compound interest. Okay, Julie receives the scholarship of $5,000. Okay, and she's going to start uni and invest it for 4 years so that she can access it before moving out of home. So she doesn't just invest it in the one account, she invests it for 2.5 years at 6% compounding monthly, okay, before placing all that money in an account paying 7.5% compounded quarterly. Okay, and then here's the question: if Julie had invested the $5,000 in an account that compounded yearly instead, what rate of interest would have resulted in the same final amount as above? Okay, so there's a lot of information in here. I just need to work our way through it. So we'll start with what she did do. Okay, so Julie's investment. Okay, and we're going to break it into two steps. Okay, so the first period, she started with $5,000. Okay, and she invested it at an interest rate of 6%. compounding monthly for a period of 2.5 years. So I've used this info, and compounded monthly, and the 5,000. I need to find the amount she has after the first 2.5 years. So I'll write my compound interest formula. Okay, and I'll substitute in these values to find out how much was left after, how much was there after 2.5 years. Okay, so she had $5,807 in the account after 2.5 years. Okay, and then there's this second period, okay, where we don't know how much she's going to end up with, but she's investing this amount, okay, this amount that she had after 2.5 years. She's going to invest in an account that pays 7.5% interest. Compounding quarterly. For how long? Well, 4 years total. She's already used 2.5 years. So 4 minus 2.5 equals 1.5 years. Okay, so I've used this 4 years. I've used 7.5%. I've used the compounding quarterly. Okay, so from here I need to find how much she'll have at the end of this extra 1.5 years, using again my compound interest formula. Okay, and just substituting in all these values. Okay, to see how much she'll have after 4 years. So I found that she has 6,491 after the 4 years. And I've put a little bit of extra C&J around the place as well. Okay, the final part of this question is if Julie had invested the 5,000 in an account that compounded yearly instead, what rate of interest would have resulted in the final amount as above? Okay, so this is sort of one section complete. Okay, so what is I if the 5,000 was invested compounding yearly? And that's a question we need to answer. Okay, so I'll have a go at that. So we need the final amounts to be the same. This is probably the key part. So we need that final amount. We're still investing that same amount. Our interest rate we don't know, but we're compounding yearly for a period of 4 years, and we need to solve for I. So the formula is as per usual. Okay, and we'll slot in all of these values and see if we can go ahead and solve. Alright, so I'll just write these steps in. Trying to get I by itself, I'll divide by 5,000. A1 plus I on 1, don't need to divide by 1. And it's the power 4. Need to take the 4th root of both sides. Okay, ideally it should be plus or minus again. Okay, because we're taking the 4th root. Need the 4th root of this. Should really be plus or minus. Okay. In a lot of problems, the minus will reject anyway, but that's okay. We'll see what happens. And to get I by itself, we'll subtract 1 from both sides. So plus or minus this 4th root. Okay, -1. Okay, I'll go to my calculator. I'm never going to put this plus or minus sign into my calculator. Okay, I'll just find what the fourth root of all of this is. Over 5,000 minus 1. Okay, so we got 0.067. What happens if I have a negative sign in front of this, which would be the negative solution? If I can get there. Okay, -2. Okay, so that solution doesn't make sense. Okay, we can't really have negative interest rates unless we're in Europe. Okay, so the I value is 0.067. So, okay, reject negative. Okay, as it's meaningless. Interest rate is 6.7%. Okay, there's only a plus or minus here when this power is an even number. If I had 4.7 as that power, there would be no plus or minus, only when there's even powers. Okay, unlikely to happen. Question 6 is just about drawing pictures. Okay, for the vessel shown below, sketch a curve to show the relationship between the height of the water level H and the amount of liquid added to the vessel V for volume. Provide justification for each section of the graph. Okay, so I'll zoom into this nice and big so I can all see it. I'll draw a graph beside it, and I'm looking at the height of the water level versus the volume. And I'm imagining water coming in there. Okay, some water, some fluid. For this first section, okay, it's going to be going up at a constant rate. Okay, so until I get to sort of this height, just the constant rate. Pretty slowly, because this is a pretty big base. Okay, in this section here, the bottle is getting narrower, so as I add volume to it, the rate at which the height increases is going to get faster. Okay, so we'll see some sort of increase like that, getting faster, and then it gets wider again, so we can see it getting flatter. Okay, but probably not that flat. Okay, and from this period onwards, we've got a constant rate of change. Okay, but note that it's going to be faster than this one because the thing is narrower. So something like that. Okay, note that these two are different steepness. Just rubbed it out, that's good. Okay, and then in the top section, again, getting much narrower as we go there. So again, it'll be increasing the rate again. That probably shouldn't be that steep. Probably more like that, just slightly steeper than the other one. Because here I need to show an increase. So a slight increase in the rate until I get to this section where it's going to be completely flat again. Okay, as the bottle's filled. Okay, so if I was trying to justify what's going on here, I'd probably divide it, okay, into these sections so that we can actually see what's going on. I call this section 1, section 2, section 3, section 4, and section 5. Okay, and I'd write a comment about what's happening at each of those sections. Try and do that beside here. Okay, so there you go. There's some written comments divided into 5 sections and written about each section. Okay, probably the key points are to mention the constant rates of change, okay, and these ones about why it's steeper than S1 and why this is steeper than S1 and S3. Okay, they're probably the key points to note. Okay, question 7 is a graph about temperature and time. Okay, part A, what type of rate of change is occurring and justify why? So we've got 2 different rates of change, constant and variable. Okay, this rate of change is not constant. Okay, not constant at all, because going down here would be pretty exciting. Okay, this red line is not constant rate of change. It's different. Okay, here's really steep, here's really flat. Okay, so we'd write there is a variable rate of change. Okay, as the average rate of change from in one section is different to the average rate of change in the other section. For part B, find the average rate of change of temperature between t equals 2 and t equals 6. So t equals 2 is this point, t equals 6 is this point. I want to find the average rate of change. So what's the slope of that line that passes through those 2 points? Okay, so my 2 points are 2, 30, and 6, 6. I'll call this T1, T1, and T2, capital T2. And I'm trying to find the average rate of change. I don't know the formula, so my average rate of change is going to be the change in temperature over change in time. In this scenario, capital T2 minus capital T1 on T2 minus T1. So let's have a look. T2, we're just subbing in values here now. Hopefully I don't make any mistakes. Minus 24 on 4 equals minus 6. What are the units going to be? We just grab the units off both of these. So degrees and minutes are going to be my 2 units. Degrees per minute. Does that make sense? Let's have a look. Yeah, okay, it's going downhill. Downhill means negative gradient. Sounds good. Okay, 6 degrees per minute. Part C, determine the instantaneous rate of change at t equals 4. Again, we don't know the formula. Okay, so instantaneous rate of change is going to be the slope of this tangent. The way we'll find the slope of this tangent is by just using any 2 convenient points. Okay, I'm going to use this point here, which is 0, 30. And why not use the point that's actually on the line as well? Okay, it's a nice convenient point, 410. Okay, so for part C down here, we'll just write something to show our understanding. The instantaneous rate of change is the slope of the tangent line at that point. Okay, so what were my 2 points? 0, 30 and 410. And 410. So I need to find slope or gradient between these 2 points. Okay, again, T1, T2, correction, T1, T1, and T2, T2. So my instantaneous rate of change, IROC, change in temperature on change in time, exactly the same scenario as in that previous example. Whatever minus 20 on 4 is. Okay, I think it's minus 5 degrees per minute. Okay, again, let's look back, make sure it looks reasonable. Yeah, it's negative downhill. Yeah, it's probably less steep than that one, a little bit less steep. Okay, so we're all good there. I better keep this point in for the written solution. Okay, so this one is for part B, correction part C. And this other line here was for part B. Okay, all good. Alright, so we've got a particle moving along a horizontal straight line. Okay, here's some point 0. The particle starts at a point 20 meters to the left. Okay, so it starts at this point, which we're going to call negative 20. Here's my particle. Let's pretend it's a person. The displacement time graph for the motion of the particle is as shown. So this guy comes from minus 20 to a little bit past the origin, so he'll go like to here, and then he'll decide to go back to minus 10. Yeah, and then he'll turn around again and keep going. That's about as far as we know, but presumably he's going to keep going in that direction. Okay, so, you know, pretty practical problem. We have to draw velocity time graphs. Actually, I'll leave that in. That was a good diagram. Come back. Leave that diagram in. So you can see, just by looking at this graph, here he stopped and turned around, and here he stopped and turned around as well. Okay, in this section here, his velocity is going to be positive, okay, because he's going from left to right. Similarly in here, a positive velocity, whereas in this middle section, it'll be a negative velocity. Okay, so I've got these three axes. I look at this graph and I think straight away, oh, it's a cubic. So when I find the slope of it, if I find the rate of change, which is what velocity is, I'm going to get a linear function down here. Correction, quadratic function down here. Okay, is what I'm guessing. Okay, the way I'm going to find this is just using some slope lines. Okay, I'll always start by finding where is it completely flat. So it's completely flat at this point and this point. So I'll mark them on my slope function as being flat points. Okay, so I've used that information. Is this point anything important? Okay, no. In terms of my velocity time graph, not at all. Okay, I don't care that he's just passed the origin for the second time. It doesn't matter. In fact, pretty much these axes are completely irrelevant at this point. Okay, maybe I need the horizontal one, but the vertical one doesn't matter anything to me at all. This could be happening anywhere. I'm just looking at the slope all the way. So at the start, we had like a really steep positive gradient, then it got less steep, and then eventually 0. Okay, so I'm going to draw initially some positive gradient, then some less positive gradient, okay, eventually getting down to 0. We'll have a look what happens in this next period between these 2 points. So a negative gradient, a steeper negative gradient, and then a not so negative gradient. So let's have a look, how can I do that? Down here, a negative gradient, a steeper negative gradient, and then a not so negative gradient. Okay, it should probably be a little bit more curved. Okay, and then afterwards, a positive gradient, a bigger positive gradient, and a bigger positive gradient. So the gradient just keeps getting more positive as we go up here. Okay, so my one sort of looks like a V, but we want to try and get some sort of a parabola shape going, if possible. Okay, so it looks something like this, our velocity time graph. Okay, we'll see if it makes sense for the story above. So he started going at some velocity at about 2, he stopped. Yeah, 0 velocity. And then he came the other way with negative velocity. Then he stopped again. And then he's going on his way. Okay, so always check that your story makes sense Remember, we're just telling stories with graphs. So from velocity to acceleration, okay, is again the rate of change. Remember, the acceleration is the rate of change in velocity. So I'll just write these two understandings here somewhere. Okay, remember, velocity, rate of change of displacement, acceleration, rate of change of velocity. Okay, and again, I've got a quadratic function here that I'm finding the rate of change of. This is going to end up with a linear function, okay, as a check. So I'm just finding slopes down here. It's probably a little bit harder to think about acceleration for some of you guys that don't do physics, but we'll just find the slope exactly the same way. I'll find a point where the change in velocity is 0. Okay, so I'll just mark that point on the axes, and then I'll look at the slopes either side. So if I look here, this is a negative slope. Okay, it starts off really negative, okay, really steep, and then gets less steep as it comes to 0. Okay, so this is going to be a linear function, straight line going down. Okay, don't make the same error that I made just then. Okay, it's a negative slope. Remember, this is telling me the slope. So it starts off as a negative value. Starts off as a negative value and gets less negative as we go up. Okay, remember this vertical axis is telling me the slope of the thing above it. As we go here, positive, increasing positive, getting even more positive as we go up. Positive, positive, even more positive in a linear fashion. Okay, so that'll be my acceleration graph. Okay, so this is the slope of the VT graph. This is the slope of the ST graph. Okay, that's it. Good luck on the final exam in heaps of time.